Welcome back, folks. So we'll go through multiple regression and I'll talk about dummy variables. We'll use it for the case. It's more for your lab. And then I'll pause the video and then I'll do one more recording. This has me working through the examples for the applied element. And then we'll conclude session 2 learning. I'll also show you a tool. It's not in your book. It's relatively inexpensive for those who are wanting additional statistics resources. I'll show you that. I went and pulled this off my bookshelf. We are kind of scratching the surface with regression. Being that you all have had it a while back in statistics, but it's about 700 pages on just regression and different types of assumptions, rules, logistic. So if we're going to predict a category versus a continuous variable, how we go about doing that. The reason for showing you the book is to hopefully illustrate and show you it can get a whole lot deeper than where we will go, but and even beyond what your textbook. But it's a very useful analytic technique. Okay. All right, without further ado, here we go. So when we look at multiple regression, we're looking at how multiple predictors adjust the fit of the line. And per last class, I said we really don't do things in 3 and 4 dimensions because it gets a little complicated, right? And so that's why we don't necessarily chart out a scatter plot data and draw a line from that per se when we start talking about multiple regression. But what we are looking at is the independent predictors to hopefully significantly play a role in explaining variance on the dependent variable, i.e. the outcome variable. Okay, so obviously the regression equation is, we still use the least squares method. Okay. A newer thing, which I brought up in the first part of this video series, is we'll calculate another coefficient, i.e. slope. Okay. And so if we hold one constant, we could put our value in for another coefficient and we could kind of see what that value might be, right? So we can hold constants, or we can hold slope values, coefficients, we can hold them constant with like a 0 or a 1 if we don't have all those data points. So there's some regression models that may have over 20 independent predictors. Okay, you need more data for it, but you can do that. Which leads back into the point that the student brought up in our last session. Using the adjusted R-squared as more of a litmus test to see if it's increasing and adding value. Right? We still will report the regular R-squared. Right? All right. So what exactly is the coefficient? Well, it's an element and variable that shows uniquely how, when it's a part of the model, how it plays a role in variance considering other variables. So I'll say it again. So it's an element, i.e. variable, when incorporated with other variables, it plays a role in explaining variance. Just because you remove, say we have 10 independent predictors or independent variables. Just because you move one doesn't mean the rest of those values will stay the same. The coefficients will change, right? So, and potentially by removing one of the predictors, it could say it was not significant and you had 9 that were significant. By removing one, possibly it could flip the sign of one or several others to be not significant. So when we start talking about multiple regression and those coefficients, it's how they kind of work together, or how they're associated, right? Specific to the slopes and coefficient. The constant will change too for each variable that we add or remove. It plays a factor on the intercept or the constant. Okay. So we have regression coefficients, and I guess one way to look at how we explain them is a 1 unit change in that unit is a percentage change on a dependent variable. So I'll say that again. A 1 unit change on the independent, what you're seeing on the coefficient is the percentage or the value change on the dependent variable. Okay, so let that sink in a little bit, but that's what's going on. Okay. I'm going to bring this up here shortly, this example, and walk through it with you and how we can populate this. I tried loading stat tools. I've got a different computer here at my house, and my other one, it works fine with this one. It's a little faster on the RAM. In particular, the stat tools isn't running on my faster computer. So we'll do it the data analysis way, which will be fun. And we'll go through and do a quick regression as we're looking at this particular problem. It's on page 430. Here's the solution, right? So it says estimate the equation for the overhead cost at Bendrix as a function of machine hours and production runs. So these are our two independent predictors, and we can see that right here. There's the intercept, okay? And we're looking at what the R squared is, okay? Here it is, 0.86. And then we've got our adjusted R and our standard error, okay? And if we were focusing in, we would say these are both significant predictors, so it looks like these are adding value. Okay, and so it gets into the next part. Well, how do you interpret this? Right, so we built out this equation. And so for each 1 unit of machine hour increase, it adds 43.54 to our overhead. So a 1 hour increased machine adds 43.54 to the overhead, okay? A 1 unit increase in production runs adds to 883 in overhead. Okay, so that's how you interpret that. And obviously, and then we would add up our constants. So if we had, here's a higher level picture. If we had just the equation, what's the overhead if we did not have machine hours production runs? Looks like almost 4,000. Okay, that's how we would interpret that. If we zeroed and held these both constant, hours and runs, we would just report that. All right, so I can find it. Here's the overhead. Hey, come back. So walking through step by step. Okay, so I want, here we go. Overhead. Go to your data analysis, right? So go to data in the menu, data analysis, and we're going to click regression. Y is our independent, so I just click on that and you can hit Control Shift down and that will get the column for you. And now we need our independent predictors. So Shift, arrow key over, Control down, and that will get those 2 columns. Okay. Select your labels because we've chosen row 1. Like I shared with you last time, you automatically get the 95th percentile, but let's move it to 90. Let's look at our residuals and standardize. more for populating purposes. Okay, new worksheet, click OK. And there we go. And so if we were to compare, let me bring this back up. What they populated out of stat tools, we've got the same answer, right? Here's our 86. There's an 86.64. Let's look at our coefficients, 43 and 883. So we just did it the same. From what I have looked at stat tools, you can get some nice looking graphs, but you have to goof around with the data a little bit, right? But I would highly recommend using the data analysis add-in that we've already established for you, right? So, and I've already went through what this means in our interpretation. That's the important piece whenever we're looking at doing statistics is the interpretation. So it's one thing to crank it out, but we got to understand what it is that we just cranked out, right? The standard error in the on the intercept, that's not too concerning, and for the value of the standard error on that coefficient and production runs, relatively not too concerning, right? As a percentage of the coefficient, it's relatively small. I was giving you out some values, and we can go through how you calculate the p-value in the stat or the t-stat. It's a little bit beyond what we need to do in this class, but as a percentage of our standard error of the coefficient, it's relatively small, right? So not too concerned on that. But you did see, though, you bring this up. This is a website that if you want to dive in more to statistics and learn beyond this class, I don't know what the memory, I think it's like 10 or 15 bucks a year, right? But it is extremely robust whenever you say, well, what tool do I use? So what quantitative tool do I use to solve a problem, right? This is built around SPSS, and I know we're not using that in this class, but so it has all of these particular statistical tests. It's kind of like you're not going to go change a tire with a crowbar, right? You'll use normally a socket, right? So these different tools are how you handle different quant problems. So if we go to regression, we have assumptions that have to be met. Okay, so it needs to be linear. The residuals can't be correlated, right? So the standard errors can't be correlated. If that's the case, then we got a bust. You got really this. They lay out 7. Really, is about 4 assumptions that have to be met for to use regression. If it say you get a bust on one, what do you do? Well, normally you go into the transformation mode. Again, beyond this class, but you transform your variables. You can use a log. And when you do that, it's a way to address the violation of the assumption because it's a little bit more stringent. Okay? And so you can kind of come through here and say, okay, well, I'd like to look at the assumptions. And these guys have done a great job. They're out of somewhere in Europe, right? So we talked a little bit about this in class. So this is curvilinear, right? And this is a U-shape. That's a problem. So curvilinear is a problem, and a U-shaped curvilinear, that's a problem. And so it gives us a way that how we handle these. Okay. Not doing a sales pitch for SPSS or Layard statistics, but I did want to bring this to your attention. Has a nice little menu-driven system if you want to try to figure out what type of statistical test to use, right? You want to do group differences, that tells us it's a t-test, right? So association and correlation. Okay. So ANOVA is when we have more than two groups that we're trying to evaluate, which I brought that up in our first time together. All right. Anyways, back to our topic here. So when we get our standard error that I showed you on our data that we just ran, it's obviously similar to a simple regression. And it is the standard deviation of the residuals, right? So if we look right here, and you'd say, well, do we need to calculate? Well, your software will calculate it for you. We use this as a way to gauge, since we're not necessarily looking at all the data, how high is too high, right? It introduces standard errors, help us to identify if we have type 1 or type 2 error. I won't go into it right now. I'll go into it a little bit later. But if we have a lot of error, it lets us know that it can be either type 1 or type 2. So I'll leave it at that. If you want to look into it more, feel free. Okay. Here's the adjusted R, right? Helps us to see if we've got usefulness in our explanatory variables that are added. But I do want to tell you this. You may find one that's not significant. And that by itself is not grounds to start removing a variable out of a model, because it may play a role, a confounding role, or an interacting role, which could drive another variable. Okay, so just because it's not significant, it doesn't say, well, trash that one. Not necessarily. Okay, maybe. So we have several different types of explanatory variables, right? Dummy, so that's where we turn a binary, like we turn a category into a 0, 1. Or I was telling you in our first meeting together how we can turn variables on and off. That's a dummy variable, right? Interaction variables. Those are kind of really unique. I won't cover it today. We will see that on the 24th. Interaction and nonlinear transformations, which I've already kind of alluded to. That's how we deal with them, right? And this is towards the end of chapter 10. Okay. So dummy variables. Categorical. Typically a 1 means it's on and a 0 is off. Okay. When there's more than 2 categories, you can and will see that in your case, how to handle that. But typically we only use it for 2 categories, right? All right. Let me get this loaded. Before I load it, we'll kind of do a high-level look from the screenshot. So in your textbook starting on page 443, there is a example, right? So it says possible gender discrimination in bank salaries. Objective, analyze whether the bank discriminates against females in terms of salary. Solution, data set includes the following. We look at it educational, so it's a categorical. We look at grade, years, experience, and salary. Okay. So I'll populate that data here shortly and let you look at it. So what do we need to do? Create a dummy variable for the categorical variables using if functions or the stat tools. Then run a regression analysis with salary as the dependent variable using combination numerical and in dummy explanatory. Don't use any of the original categories such as education. Always use 1 fewer than the number of categories, right? You all have the deck. This is out on D2L. When we do that, we get this output. So essentially we're turning on if education 1, a 1, else 0, if education 2, 1, else 0. I'll show you the setup on it. And then we run a regression, and here's what the output is. And so on a high level, we can see it looks like education 4 is in a significant predictor, okay? Whereas everything else is playing a role in gender discrimination. So based on the more education, it looks like it plays a role in reduced discrimination, the way I would interpret this, okay? So somebody that has 1 year of education, lower degrees, or a lower outcome. Okay. Okay. You have this in your textbook, and so it's going to give you the same information I'm going to show you right here. But it's more for like the if statement, right? So these categories here are not populated in your data, and these would need to be calculated, right? So here's your if statement. And the way to read that, based on if gender, so we're going to call it categorical, right? If it's a female, then populate years. And if not, it's a 0, right? So and since this right here is a male, it's given a 0. But for each female, it's only going to populate for females, right? And once we get these values, it's taken the log. In the essence of time, because it's I'm at 22 minutes, there's a time and place, and the reason we're using this is we kind of have to adjust a categorical variable, and so that's why we're using this log measurement. So anyways, moving all the way through, we can look at different data points. Obviously, these were calculated out of stat tools by looking at this is kind of a little bit of a concern when we start seeing a fan like this, right? So we don't want to see fans. Not a good deal. Relatively, this predicted, we're getting someone, they're not really grouped like we'd like to see, so we're kind of getting a little bit of a fan, which is kind of indicative of number 4 here. Not too bad. And again, we're starting to see, for prediction purposes, we can see the trend up, but I would say there's maybe a little bit of concern. This was real data from the author, so you're going to get some noise within the data. We can tell a little bit about this because the R-square, right? And what's happening when we add more variables in, it bumps the R-square. Look at the adjusted R-square go from 0.63. It's going up too because we've added more variables, and it drops again. So just by kind of looking at your data charts here, I can get a feel of what the data is, if it's going to be having a decent fit or not, right? And this is confirmatory right here. So these visualizations go hand in hand, right? We may see a little correlation up here, right? So that obviously this is kicked out of, again, stat tools. And here is kind of like an interpretation from the textbook, which is already in your book. So I'll wrap this part up, and then I'm going to make a video on working through the case and a couple of the assignments I handed you, gave you to practice on, and then look forward to seeing you on Monday. So here's what we got. For Monday, the 24th, what I will be covering is modeling possibilities. So the interaction, we'll go through that, and we'll look at nonlinear. Then we'll shift gears and get into chapter 11, and we'll look at the statistical model and regression coefficients. Expand on that. Your homework number 1 is due. Check out D2L so you can see that. And then I'll do a class demonstration on your homework. So let's see here. When we get to the 31st, we've got quite a few things that we cover. Multicollinearity, include, exclude decision, stepwise regression. So a stepwise is when we add a variable and then we add another variable and we start looking at increased model fit, start looking at how the R-square, how does the model tighten or does it get better? So it's in steps, right? We got a case, which will be in class for participation. And then I'll release out your homework number 2. So that's in 2 weeks, roughly. And that will be due on February 7th. So that's all for this video. And I'll do some demonstration coming up. Thank you.